Hi guys, let's talk science. So, the last time we were together was almost 3 weeks ago. And the last time you were in physical science, I wasn't there. So I want to just kind of recap 6.1 with you before I give you more time to work on 6.1. So I just kind of want to chat as best as we can. Here we go. So you should have done the chapter question. That's pretty straightforward. But I want to just review some of these words with you. So this is just like the printout version of what you guys look at. So you guys already know this stuff. I know you know this stuff. Here we go. Okay. So what are we looking at here? Okay. So you guys already know the main parts of an atom, right? So if the whole thing is an atom, we already know that the nucleus is the stuff inside of it. What are the two things that are inside of it? You guys already know. It's the neutrons and the protons. And then we have the electron cloud around it. So we've just got the two pieces. We've already reviewed nucleus, atoms, but what's an isotope? Do you guys remember what an isotope is? We've talked about this, but it's just been a minute. So an isotope is when it's the same atom. Like I just made these isotopes up. We have carbon 10 and carbon 12. It's the same atom, but there's a different number of neutrons. So like here we have 6 protons and only 4 neutrons. But over here we have 6 protons and 6 neutrons. It's the same atom, just with a different number of neutrons. That's the definition of an isotope here. So we're just kind of reviewing here. We got nucleus, atom, isotope. Do you remember what mass number is? Mass number can be told from our periodic table. So mass number, let's see if you can see this here. Can you see this? Mass number is this number right at the top. Like this is sodium, Na is sodium. That mass number, is at the bottom. I'm lying to you. Mass number is how many total protons and neutrons are in the nucleus. So like the mass number here for sodium would be about 23. Do we remember what this top number here is, this 11? We call that the atomic number. This is also the same amount of protons that are in the nucleus. So just to recap, we've got the whole atom has a nucleus. Inside of the nucleus is protons and neutrons, and around it is the electron cloud where the electrons live. This is all review. It's just been a minute. So just a little notes, I guess. So the mass number is the number of protons and the number of neutrons. So protons and neutrons, if you add them up, they're going to give you the mass number. However, the atomic number is just the number of protons. So it's that usually going to be a whole number, always going to be a whole number. So let's get into what you did the last time you were in physical science class and I was not. You were asked, you've seen this before, just like way back in October or November, maybe even September, guys. So I literally just copied and pasted from one of our old notebooks just so that we could recap, because this skill is super important to know for later. So looking at the periodic table, we could fill these out. So I filled some of them out just so you could check your work. It's actually kind of hard for you to see it. But we'll go over one together and then we'll fill the rest out as we go. So like here's an easy one to start with is sodium. The atomic mass, can you see it? The atomic mass of sodium is 22.99. We get that straight from the periodic table. So sodium, we're gonna find it, over here. Sodium, that atomic mass comes right from the periodic table. That's 22.99. 22.99. So we're just going to fill out 22.99 here for the atomic mass of sodium. Next, it asks us for the atomic number. Atomic number also comes straight from the periodic table. It's that whole number at the top. So we find sodium again on the periodic table. Where are we? Here you are. Okay, we find sodium again on the periodic table, and it's 11. So we're going to say, okay, the atomic mass is 22.99 of sodium, but the atomic number of sodium is 11. This number, the atomic number, is going to tell us the number of protons. So if we know atomic number, we know the number of protons. So if the atomic number is 11, the number of protons is also going to be 11. And guess what? In a neutral atom, which we are assuming that it is, we can figure out by the number of protons, we can figure out the number of electrons. So we've got number of protons is 11. We're going to use this. I hope that this is, oh, okay. Hopefully that fixed it. Where's my pen? Okay. So if the number of protons is 11, the number of neutrons, we don't know yet, but the number of electrons should also be 11. I just want to make sure that we're still recording. Okay, awesome. So number of protons we know, which means that we can fill in number of electrons. Okay, now the number of neutrons, we need to do a little bit of math. Number of protons plus neutrons should equal atomic mass. So this atomic mass is 22.99. We cannot work with a decimal. We're gonna say, for easy purposes today, we're gonna say, okay, 22.99 rounds up to 23. Okay. So we're saying that protons plus neutrons should equal 23. So we know that protons is 11, so 11 plus something equals 23. And if we work backwards, we say, okay, that something is 12. So I've worked with you on just the sodium one, just kind of running through an example that I've already done. But I want to work with you on the last row. We won't, you can decide if you need to fast forward or whatever. If you need the review, stick around. If not, you can fast forward. We're going to work on this N. So N is for nitrogen. So I'm going to fill that in. You can fill that in too. We've got nitrogen. There we go. And first question, it says, oh, what's the atomic mass? So we're gonna go to our handy dandy periodic table. You can just Google one if you want. I don't remember if I gave one to you in the notebook, but we're gonna look for nitrogen on our now wet periodic table. Here we go, nitrogen. Oh, there we go. All right, so the atomic number of nitrogen is 7, and the atomic mass, can't read backwards, is 14.01. So that's what we're gonna put in nitrogen. I'll try to write. So the atomic mass, can't do that, is 14.01, and the atomic number is 7. There we go. Okay. So if we know the atomic number, then automatically we know the number of protons, because that is literally what the atomic number tells us. So if the atomic number is 7, then the number of protons is 7. This is all review, you guys. Nothing new here. And if it's a neutral atom, which we are assuming that it is, the number of protons is equal to the number of electrons. So I'm going to fill that out right there. Here we go. Now a little bit of math required. So protons, where am I? Where's the pen? There we go. Protons plus neutrons is equal to atomic mass. So 7 plus something is equal to 14.01. Let's say, oh, that's 14, okay? Because we can't have a fraction or a decimal of a neutron. So 7 plus something is equal to 14. Well, that something is 7. So there's going to be 7 neutrons. And this is what our completed nitrogen box looks like. Moving on to Fe. Do you want to take a guess? I heard somebody say iron. Awesome. Want to play with snow? Yeah? Okay. No? Iron. What is the atomic mass and the atomic number of iron? Well, let's go. Iron's right here. We've got an atomic number of 26 and an atomic mass of 55.85. So I'm just going to take some time. We've got an atomic mass of 55.85 and an atomic number of 26. If we know the atomic number, we know the number of protons. 26. And if it's a neutral atom, which we are assuming that it is, if it's a neutral atom, there we go. If it's a neutral atom and we have protons, then we know that the number of electrons will match. Do you want to make a debut? And if we know, okay, goodbye. If we know the number of protons and the atomic mass, we can figure out how many neutrons. So 26 plus something is going to equal the atomic mass. And in this case, we're going to say, okay, let's say that's 56. So 26 plus something is going to equal 56. I'm going to put in 30. How are we doing here? Okay, looks good. Let's do one more together. So we just did nitrogen, we just did iron. Let's do aluminum, that's fun. All right, so Al is aluminum. And we're gonna figure out, using the periodic table, the mass number and the atomic number. So where are we? Oh, there we go. Aluminum right here. We have an atomic number up top and a mass number on bottom. I'm gonna record that right from the periodic table. So we've got 13 as an atomic number and 26.98 as a mass number. So if we have the atomic number, we have number of protons. So if the atomic number is 13, then the number of protons is also 13. And if it's a neutral atom, which we're assuming that it is, the number of protons, which are the pluses, the positive pieces, subatomic particles, those should be equal to the negative subatomic particles, the electrons. So if there's 13 protons, there's 13 electrons. And now we've got this. So if we have 13 protons, but the mass, the atomic mass is 27, let's say. So 13 plus something equals 27. Well, what is that something? It's going to tell us the number of neutrons. We have to do a little bit of math. So should we get 14? Did I mess it up? 14 looks good. Okay. And we've got our finished square. If you are struggling with this, let me know. Like, we can work on it again in class. I know it's been hard because like we haven't really touched base like face to face. But if you're ready to move on, like if you fast forward it, you can pause here. So we're practicing this because it's super important, and what we're learning next is about like decay and stuff. We also need to review isotopes. Isotopes, like we said earlier, is, everything's wet now, is when an atom has the same number of protons but different number of neutrons. Because remember, if it had a different number of protons, it wouldn't be the same element anymore. So we have carbon 12 and carbon 10. They're both carbon, so they both have 6 protons, because according to the periodic table, it needs to have 6 protons, right? Carbon is right here. The atomic number is 6. That means that it has to have 6 protons. If it had any other different number of protons, it would not be carbon. So these two are isotopes because these atoms both have 6 protons, but a different number of neutrons. So if you count it, there's actually 4. Oh, I just wrote it out wrong. There are 6 neutrons here, and there are, oh, I did write it out right. I just am reading backwards. Okay, here we go. So carbon 12 has 6 protons and 6 neutrons. Protons and neutrons equals that mass number. That's exactly what we just practiced here. Protons plus neutrons equals mass. Protons plus neutrons equals mass. So if there's 6 protons in each, but a different number of neutrons, then the mass is going to be different. So carbon 12 has 6 protons, 6 neutrons, 6 plus 6 equals 12. But carbon 10 has 6 protons still, but only 4 neutrons. So we just had to do a little bit of math. These are isotopes. It's the same atom, same number of protons, different number of neutrons. So back in September, October, maybe November, I don't remember, we practiced isotope notation. This is something that looked really ugly, but you guys had got the hang of it super, super, super quick. So I did 2 just to kind of chat through them, but we can do the bottom ones together. So it says, what is the isotope notation of chlorine 37? This top number is going to always be the same number that's in the name, because chlorine 37 is telling us the isotope. This is how many protons and neutrons there are. This is telling us the mass number of chlorine isotope. So 37 is going to go up top. And then this 17 comes straight from the periodic table. Chlorine There we go. Chlorine has an atomic number of 17. And that's what it's asking for here. It's just asking for the atomic number, aka the number of protons. So 37 comes straight from the name, that's the mass number, and 17 comes from the atomic number. So I can actually write that. So this is the mass number, and this is the atomic number. This mass number is going to come straight from the isotope name. Doesn't matter what the periodic table says. So we have chlorine 37. That means that there's 37 total protons and neutrons, and there's 17 protons. So when we go over here to figure this out, well, number of protons is given to us by the periodic table. There's 17. And in a neutral atom, which we are assuming that it is still, there should be the same amount of electrons as there is protons. So 17 electrons, 17 protons. Now we need to do a little bit of math. The number of neutrons and the number of protons should add up to that mass number being 37. So something plus 17 is equal to 37. Well, what is that something? 20. Let's look at the next one. It says, what is the isotope notation of chlorine 35 this time? So 35 is going to go right up to the top. That's the mass number. And chlorine didn't change on the periodic table, so we still have 17 as an atomic number for chlorine. There's still 17 protons, so 17 is still this bottom number because it's just the atomic number. That doesn't change. So we have 35 total items in the nucleus. 17 of those are protons. So we're going to go over here. There are 17 protons, 17 electrons. Now protons plus neutrons should equal that mass number. So 17 plus something equals 35. What is that something? 18. 17 plus 18 equals 35. Let's do one completely undone. Let's jump down to magnesium. We have two isotopes here, magnesium 24 and magnesium 25. So it says, what is the isotope notation of magnesium 24? Well, we need our handy dandy periodic table. We're going to find magnesium right here. Right here. Magnesium has 12 for an atomic number, which means that it has 12 protons, which I think I'm getting ahead of myself actually. So magnesium 24, sorry, it's just hard to see. I'm working backwards here. Magnesium 24 means that this top number is going to be 24. We get that right from the isotope notation, 24. Magnesium 24 means that the atomic, that the mass number is 24. And the atomic number is 12, so we're just gonna put that right in. If the atomic number is 12, then we know that there's 12 protons, and if there's 12 protons in a neutral atom, then we know that there are 12 electrons. Now, neutrons, we need to do a little bit of math. 12 plus something is going to equal this mass number. 12 plus something is going to equal this 24. Well, what is that something? Just so happens that in this case, it's also 12. But there's a different isotope over here, also of magnesium. It says, what is the isotope notation, this time of magnesium 25? So 25 is going to be this top number. That comes right from the question. And the atomic number of magnesium didn't change, so this is still going to be 12. There we go. And if the atomic number is 12, the protons are 12, and if the protons are 12, then the electrons are 12. Now we need to do a little bit of work. So protons plus neutrons is going to equal this mass number. Well, 12 plus something is going to equal this 25. What is that something? It's no longer 12, it's going to be 13 neutrons. So these two are both an isotope of magnesium. They both have 12 protons, but a different number of neutrons. They're both magnesium, but one's magnesium 25 and one's magnesium 24. So they're different isotopes. Okay, moving on. The reason why we had to review this is because I want to talk with you about radioactive decay. You guys know that this is coming. I know that we're excited. I know that we're ready to watch that HBO miniseries, but we have some work to do before. So decay is not rot. Decay is not rot. If I say, oh, that apple decayed, you might like say that in real life, but this is not what I'm talking about. So decay, you can use the definition that's in our glossary, like in Canvas, but just to walk through it so that you have something to look at. Decay, first of all, is not rot. It is when an unstable atom tries to stable itself through one of three processes. So there's 3 different types of decay, and we're going to talk about all 3 of them, but today we're going to focus on one specific one. So it's when there is an unstable atom, it will naturally undergo decay. This is not rot again. It is when an unstable atom will undergo one of 3 processes that will help it find a more stable state. This decay will only happen when an element has a ratio of protons that is nowhere close to 1:1. So what I mean by that is carbon 12 and carbon 10 are both isotopes. Carbon 12 has 6 protons and 6 neutrons. That's a 1:1 relationship. There's 6 protons and 6 neutrons. That's a 1:1 ratio of protons to neutrons. Because if you reduce it, 6/6, you get 1/1. That's the math behind it. Carbon 10 has 6 protons and 4 neutrons. That is not a 1:1 ratio. So if you compared, carbon 12 is a very stable atom. It's very close to a 1:1 ratio. Carbon 10 is not. So I had other stuff that I want to show you. I guess I lost it. Let's just keep going. Okay. So there are 3 types of decay. There's alpha decay that we're going to talk about today, gamma decay, and beta decay. This is not rot. It is when an unstable atom that does not have a 1:1 ratio of protons to neutrons exists, and it will try to undergo, it will change by itself in 3 different ways. One of 3 different ways is the alpha decay that we're going to learn today, to try to find a more stable state. So you have like a little reading that's next. Watch this video, guys. You have a linked video here. Watch it. Don't just skip it, okay? I think it's worth your while. Then you have a little reading. Like, I'm assuming that you did this on Thursday before break, but just in case you did it, do it today. And then you've got a post-reading paragraph. Over on the side, I gave you a word bank, so you don't have to like read my mind or anything. Use the word bank that's over on the side. So here we go. Now the fun stuff. If you have an unstable atom like uranium, let's check out uranium on the periodic table. Oops. If you have an unstable, where is it? Oh. If you have an unstable atom like uranium, you have a mass number of 238 and an atomic number of 92. That means that there are 92 protons in uranium. That means that the remainder of this 238 are protons. That is nowhere close. Like, without even doing the math, you know, okay, well, if there's 92 protons and 92 protons plus some number equals 238, you know right off the bat that the ratio of protons to neutrons is nowhere close to 1:1. If we did the math out and said 230 minus 92, do we get 140? 148? No, I made that up. 146. So 92 protons and 146 neutrons. That's nowhere close to a 1:1 ratio. This is an unstable atom. Unstable atom, nowhere close to a 1:1 ratio. So it is going to undergo something called alpha decay. So I have drawn, and I know that this is kind of crazy, I have literally drawn 92 protons and 146 neutrons. We have a mass number. We have an atomic number. This is exactly what we've been practicing. This is an unstable atom. It is going to undergo a natural process that it's going to attempt to stable itself. And it does this by popping off a helium atom. The helium atom literally goes, bye. Like, I'm tired of this, Grandpa. That's what it says. So this helium atom pops off. There was 2 protons and there was 2 neutrons, but it kind of just like is like, I'm out of here. I'm tired of this, Grandpa. So a helium atom pops off. Hang on. There we go. So we had an unstable atom, and this helium atom just decides to like, bye, Felicia, and Grandpa lets her go. What is left over is still an element. We call this the daughter isotope, right? Because it's kind of like an offspring. So let's go back to the periodic table here. If we have uranium, where is she? There we go. If we have uranium and she pops off a helium atom, well, a helium atom has a mass number of 4 and an atomic number of 2. That means that uranium is losing 2 protons and 2 neutrons, which means that uranium is no longer uranium, right? Because if we lose protons, you're changing the element. So if we have uranium over here, where are you? Yep. If we have uranium with 92 protons, but we lost 2 protons, we're going to go backwards 2 jumps in the periodic table, and this unstable uranium is no longer unstable uranium. It popped off this helium atom and has now become TH, that's thorium. And instead of 92 protons, we have 90 protons. So let me get a piece of tape again. So this unstable uranium went through alpha decay, and on the other side of that decay is a helium atom, 2 protons, 2 neutrons, and the thorium atom. Yes, it still has an uneven, not 1-to-1 ratio of protons to neutrons, but it is not as unstable as uranium was. So it's kind of like there's 2 products to this process. We have the parent isotope, the original unstable isotope, and it produces 2 atoms. It produces the helium atom and it produces the daughter isotope. Because humans love to name everything and make everything so special, we do not call this a helium atom. It is a helium atom, but it's a special helium atom. So we don't say, oh, it made a helium atom. We say instead, we call it an alpha particle, which is part of alpha decay. So when a helium atom pops off, that's alpha decay. We call that helium atom an alpha particle. Back to the notebook. Here we go. We have practiced isotope notation. Where is it? We have practiced isotope notation for a reason. I can't find it. What I mean by isotope notation is this, what we just did together. We practice isotope notation for a reason. Here is the reason. Because we're going to scientifically represent the alpha decay through similar notation. It looks kind of crazy. I promise it's actually not. So if we have an unstable atom like this cobalt, where we have a mass number given to us of 54, and okay, the periodic table tells us that there is 27 protons. This arrow is telling us, oh, it's undergoing alpha decay. And then there are 2 products. The product in alpha decay will always be a helium atom. That's the whole point. Alpha decay pops off that helium atom. She's tired of this, Grandpa. So this helium atom is one of the products always. A helium atom always has an atomic number of 2 and a mass number of 4. So all products of alpha decay will have helium and then the daughter isotope. That daughter isotope can be determined by our handy dandy periodic table. So if we start at cobalt, we're gonna find cobalt. There we go, right here. We're gonna find cobalt backwards. And we just lost 2 protons. So we're gonna jump 2 places on the periodic table. So the products should be helium and manganese. So that's where this is coming from, this manganese. Okay, so we have 54 as a mass number. That meant that there was a total of 54 protons plus neutrons, but we took 2 protons away and we took 2 neutrons away, which means that that mass number should decrease by 4. So we should say, okay, 54 minus 2 protons and 2 neutrons, so 54 minus 4, we have a mass number now of 50. And 27 protons minus the 2 protons that we took away, because helium has 2 protons. So 27 minus the 2 protons, we have 25. So that's where these numbers are coming from. So all the way down, your additional product should be a helium atom. Helium has a mass number of 4 and an atomic number of 2. And then the daughter isotope will change depending on the parent isotope, because the daughter isotope is always 2 to the left in the periodic table. Okay. Let's practice a little bit more. Let's level up here. So we have the unstable isotope, and we have everything else completely blank. We have an unstable isotope of Sg. What is Sg? I don't even know. Where is she? Where is she? Oh, here, okay. Seaborgium. Okay. So we have an unstable isotope of Sg with an atomic number of 106, so 106 protons, and a mass number of 266. So, here she is. We have, I'm just struggling to do this backwards, guys. You got this, okay. We have sigornium. And we're going to take 2 protons away from it. Where is she again? So we're gonna jump once, twice to the right, and that leaves us with Rf, Rutherfordium. Okay. So we're gonna put the notation for the element Rutherfordium, Rf, into the big square. The top square is now asking, what is the new mass number? That's this subtracting 2 protons and subtracting 2 neutrons. So this number minus 4. And then this box is asking us, what is the new atomic number? You could take that straight from the periodic table, or you could just say this number minus 2. So this is one of the products of alpha decay, is the new daughter isotope. And then the second product is always going to be that helium atom or that alpha particle. Let's do one more that we haven't done. So we have an unstable isotope of GD. Okay, so we find GD on the periodic table right here, GD. And we say, okay, it has an atomic number of 64 and an atomic mass of 158. In this case, it tells us the atomic mass. This must be an isotope. We've got an atomic number of 149. So this is going to undergo through alpha decay. The first thing we can write, because it's going through alpha decay, it's going to make the alpha particle, which is a helium atom. So I'm going to write helium, and that has 4 total protons and neutrons and 2 protons. So 2 for an atomic number, 4 for an atomic mass. That's the first product. We've got 50% of it done here. What does it make after that? Well, we need the periodic table. GD is here. We're gonna move once, twice to the left, and we end up with SM, element number 62. This is samarium. Okay, so let's do the notation. And then the top is going to come from, where am I? this number minus 4, because we have 4 less particles in the nucleus. We have 2 less protons, 2 less neutrons. So 149 minus 4 is going to give us 145. And then this bottom number is going to give us, is going to give us the new atomic number. We can say this number minus 2, or we can get that right from the periodic table. So the atomic number of this element is 102. Okay. Okey-doke. All right, one more. Let's find NP. NP. Oh, awesome. Ooh, Neptunium. That one's fun. All right, so last one that we'll do together. So we have NP is here. This is an unstable isotope. They already gave us the atomic mass and the atomic number. And it's going to give us 2 products. Because this is alpha decay, we can automatically say, well, alpha decay is going to give me an alpha particle. So I'm going to, right off the bat, without even looking at the periodic table, I'm going to say this is the alpha particle. There's 4 total protons and neutrons. 2 of those items are 2 protons. Now, because we took 2 protons away, we're going to move once, twice on the periodic table, and that leaves us with protactinium, PA, number 91. Let's just put that in the wrong spot. All right. Where are we? Okay. So PA 91 as the atomic number, but we're going to subtract 4 from 237 because we're taking away 4 pieces of the nucleus. So 2 protons, 2 neutrons, so that's 237 minus 4 gives us 233. So we have a total alpha radiation. I don't know, guys. How long is this video? I feel bad. 40 minutes. Okay, so we have a total notation here of alpha decay for this element, creating an alpha particle and a more stable atom. You guys are doing great. So I'll wrap it up real quick. We'll try to get it under 40 minutes. It was 37. The parent isotope is the original isotope, is the original unstable isotope here. So in our example, this uranium was our parent isotope. It's unstable. It needs to go through some kind of decay. In this case, it went through alpha decay. There are 2 other types of decay. We're not ready to talk about it yet. So this uranium's unstable. It does not have a 1-to-1 ratio of protons to neutrons, not even close. It's going to undergo alpha decay. Part of that alpha decay process is popping off a helium atom. This helium atom is so special that we don't call it a helium atom. We call it the alpha particle. What is left over after that is a more stable, could still be unstable, but is relatively more stable than the parent isotope, is a daughter isotope that has 2 less protons, and therefore we can figure that out by moving 2 places on the periodic table. If we've lost 2 protons, then we move 2 atomic numbers over. So just for some vocab, we have a parent isotope, the unstable, the daughter isotope, the resulting offspring atom, and then the helium atom, which we call an alpha particle. And I think that covers all of your, this is the last vocab word. So officially, alpha decay, here we go, can you see it? Okay, alpha decay is when an unstable atom releases a helium atom to find a more stable state. This will decrease the mass number by 4, right? Because helium has a mass number of 4. And if you're taking away a helium atom, then you're taking away the 2 protons and 2 neutrons. So this will decrease the mass number by 4 and the atomic number by 2 every single time. That is what I was hoping that you had done on Thursday. I know that 6.1 was super long, so that was a recap of that. For today, I think we should try to do the FET, and then we can get back together when we see each other next week. I think Monday is a green day, and we can kind of talk about how much more time we need and stuff like that. So the FET is actually pretty cool, and we'll kind of walk you through the alpha decay process. It's actually super duper quick also. Let me know if you guys need anything. Hope you guys have had a nice week off, 2 weeks. I will see you next week.